Welcome back, everyone. Thanks for rejoining us. Up next, we have Julius Zerwick, who's going to be talking about how to improve a distributed system after you have an incident. Welcome, Julius.
Hi, thanks, Jason, for the introduction. And hi, everyone. Really glad you all could come and join my talk today. My name is Julius Zerwick, and I'm going to be talking about improving a distributed system post-incident. And before I start, I do want to quickly say that this talk is going to be about an incident that paged me awake at 4 a.m. And coincidentally enough, this morning, I got paged awake by another incident at almost 4 a.m. So it seemed like the universe wanted me to be as prepared as possible to give this talk. And with that, you can get started. So I'm going to give a little background first about which is a cloud provider with a variety of offerings. Our flagship product are Droplets, which are virtual private servers. But we also offer a lot of different products as well, including load balancers, firewalls, virtual private clouds, as well as a bunch of managed solutions. At DigitalOcean, my work revolves around software-defined networking, and the team that I'm a part of actually manages an IP address management system, also known as IPAM. And at DigitalOcean, our engineering team works with a variety of microservices, uses Golang, MySQL, Kubernetes, and Open vSwitch for our software networking needs. We also use Prometheus, Grafana, LightStep, and Kibana for monitoring. And this is actually something that's pretty important for this talk. Prior to DigitalOcean, I had no experience being on call for a system. So coming to DigitalOcean and going through this experience that I'm going to share was a big learning moment for me, and I hope I can share that well with you all. So the goal of this talk is to detail a long-running incident that occurred at DigitalOcean with the service that my team manages, and it's also to describe my experience as a first-time responder. I also want to explore the takeaways and improvements that we made to our service after this incident. And then finally, to finish with the personal learnings that I have from this whole experience. And so before we get into the incident, I want to give some context to set up the incident. And that includes the service that was part of this incident. And that is IPAM, which is the IP address management service that my team handles. So IPAM is a microservice at DO that manages every IP address across all of our products. So it is in the critical path for our Droplet or VPS creations and deletes. So as a result of that, it's a service that needs to be up and running 24/7. To this day, there are about 4.2 million actively assigned IP addresses at DigitalOcean, and that goes around to 390,000 IP address assignments every single day. So this service is going through a lot of volume and has a lot of pressure on it to be functional throughout the day. But an interesting thing is that it's actually a relatively new service. It's only been in production at DigitalOcean for about 9 months. Prior to IPAM, the logic to manage IP addresses was actually part of a separate service that over time had grown too bloated with responsibilities. And we had decided it was time to split it out into a new service. And that's where IPAM came to be. And I also want to cover the architecture that involves IPAM, just so that we can all have a clear understanding of what's going on in the incident. So at DigitalOcean, if you want to create a VPS for your use, a user will send a request to our public API, which can be done either through our website or a command line tool that we provide. The request to, let's say, create a droplet will then go from the API to a microservice known as Droplet, which handles everything relating to our Droplet as a product. The request then gets sent to another microservice, which is a event queuer and processor. And this microservice will basically orchestrate everything that needs to happen behind the scenes to fulfill creating a droplet and then also tearing down a droplet. This microservice will create a work order describing everything that needs to be completed, and we'll put that work order onto a RabbitMQ cluster. And then from that cluster, we have workers that will pull work orders from the queue and then start communicating with a variety of microservices to complete these actions for creating and deleting droplets. And one of those actions is to communicate with IPAM to handle the allocation of an IP address, because without an IP address, the droplet will not be able to receive or send any network traffic. And finally, IPAM will speak directly to what we have called Alpha, which is a shared MySQL database cluster at the DigitalOcean. And so this is the flow of these creates and deletes. Don't worry if this is a lot of info. We're going to go over it again. But I just wanted to make sure we have this in our minds before we talk about the incident. And this is the path that is. And so without further ado, we will now go on to the actual incident. So this incident started with me getting paged awake at 4 a.m. on my last day of my on-call shift, which is a pretty rough time to actually be paged into an incident. The issue that was causing the incident was that droplet create events were slow to complete and eventually erroring out. And what this means is essentially that we had a lot of users who were trying to create droplets, and our system couldn't actually complete their requests. So we actually had these users who were trying to spin up a VPS for their use, but they were getting an error back saying they couldn't get their VPS. So the first team to actually respond was the event scheduler team. But after some digging, they found that their service was fine. There's nothing wrong with it. So they determined that the next team to get paged in who might be at the cause to figure it out would be the IPAM team, which is when I was paged in. And the real issue that we found was that IPAM couldn't actually finish allocating an IP address for each new droplet that was trying to be created. And because we couldn't allocate an IP, we actually couldn't finish the create event for that droplet. Without an IP, there's no way for that droplet to get any network traffic. So this was actually what was causing all these failures. And our initial investigations using our monitoring tools found that IPAM was experiencing a high latency in completing requests to allocate an IP for a droplet. Typically, we see that allocating an IP, so when we communicate with the MySQL database cluster, the latency is around 40 milliseconds to 2 seconds on a typical day. But for this incident, we were seeing latencies of over 30 seconds. So it was taking many, many times more than expected to actually try and complete that request to allocate an IP. And because this was so much longer than our typical behavior, we were actually getting 50 to 100% error rates for allocating IPs. So basically, for periods of time, we couldn't finish creating any droplets for our customers, which is a pretty terrible experience for them. And so here I want to give a few graphs to show the situation for this incident. So this is a Grafana dashboard that shows what our usual latency for the 99th percentile is for when we try and allocate an IP and communicate with the database. It's anywhere from less than a second to sometimes peaking at 5 seconds or more. But for the incident, as you can see, we had something much, much worse. We had basically a plateau of latency for allocating an IP, which is that green line that was at above 30 seconds and basically staying there for several hours. So we basically were reaching the cap of the time allowed to try and complete that operation, and it just wasn't ever finishing. And here is a capture from LightStep, which is a distributed tracing tool. And it shows the latency for these kind of operations on the left to the center on a usual kind of what we expect. And then you start seeing when the incident occurs, and we start having these huge spikes up and down, and even some periods of a plateau. So this is when the incident was really going on. And as a result, our error rate was through the roof. You can see here that we had error rates from anywhere from 40% all the way up to 100%, far, far away from what we usually expect. And so, like I said, in this entire code path to actually finish allocating an IP, creating that droplet, we have to go through a bunch of steps all the way to the end, which is IPAM speaking with Alpha, which is our database cluster. So this was really where we had to hone in and figure out what was underlying issue and how can we fix it. And we basically figured out that the issue is that because Alpha is a shared database cluster and it's shared across our system architecture, we have a lot of services that use Alpha at the same time as IPAM. And in fact, when this incident first occurred, which was late at night, we actually have our system set up to run several large queries overnight that create an increased load on Alpha. The reason why these queries are run overnight is because typically overnight in the US is our lower peak hours, so we don't have as much traffic as usual. And it's just a good time for us to run these more heavyweight queries without really affecting other services typically. But what we found was that several of these queries were being run on the right leader node in our database cluster, which they didn't really need to be. And the issue with this is that IPAM in trying to update the database to allocate an IP has to talk to the right leader node. But if it's under a lot of load from these other queries, then that can affect our ability to complete our operations. And so having these late night queries create this increased load impacted the database's ability to complete our transactions. And then that led to our create events for droplets failing. So how did we fix this? Well, when you have an incident like this, which is causing a huge impact on your customers, the first thing you want to try and is to figure out how you can mitigate the situation to restore a service to your customers, taking on some more long-term effects to either ultimately fix the problem or just kind of improve the situation. And what we first did was that we disabled our canaries across the board that were running in production. And the result of this was that it decreased the load on Alpha by quite a bit. And it was able to help us get to the point where the droplet create events could succeed, but they were still delayed. So customers could start finishing their creates and actually have VPSs to use, but it did take much longer than expected. We also moved the offending late night query that's kind of started the ball in this incident to read only. So in the future, it will go to a read replica in the database cluster, and it won't affect the write node, which is the one that IPAM needs to talk to for allocating an IP. But at the end of the day, to the root cause and try and figure out a way to prevent this kind of situation from happening again. And one of the main ideas we landed on was to look at our database transactions with IPAM to Alpha and see how we can improve that. And one of the suggestions was to switch the level of our transactions, the isolation level, from repeatable read to read committed, which could be more performant for our use case. So here's a graph just showing what I mean by that, is that when you have security and then also performance, if you have read uncommitted or read committed, you will likely have a greater performance with your transactions, but you will have less security, which means that you might have some issues with correctness of your data. And it's really up to you if you want to take on that trade-off, whereas you can have greater security with repeatable read or serializable, but then you will have worse performance. Now, changing the isolation level for transactions is not a small change. It can have dramatic impacts upon your service and what you expect your data to be. And so we were hesitant to just jump in and make this change in order to get our system back to a full functioning state. And so we debated exactly how we wanted to go about to make this change and test it, even when we were under a lot of pressure to try and fix things so that our customers could have a better experience, and also to prevent the situation from getting worse later on. At the end of the day, what our team decided was that even though we were under a lot of pressure, database operations are a critical area for IPAM, and we need to make sure that this change wouldn't cause a worse situation. Sure, our performance might improve, but what if the change caused issues with the data stored in database and we had separate issues come about? So our decision was that we wouldn't actually just move forward on the fix until we had the time and space to thoroughly test it to ensure that it wasn't going to make things worse. And as with our culture at DO, we were able to rally everyone together and basically say that, yes, we are fully fine with taking the time to test our change, make sure it's all good to go. The rest of the team would support us and make sure that the system was going to handle everything until we could get it done. So for the rest of the day, we thoroughly tested our patch and checked for any issues as a result. And we found that all of our testing looked good. We ran several different types of testing and concluded that the patch was safe to merge and deploy to production. We did volume testing, we did load testing, and we did several forms of correctness testing just to make sure that we covered our bases. And we did see a performance increase with the change to recommitted. And so we decided to go forward. And so once we made the change and deployed it to production, for the rest of the day, IPAM ran smoothly. We didn't have the delays that we were experiencing. And at that point, I was officially off call and handed the pager to my next teammate. And the status of the incident was moved to monitoring. And so at this point, we are now in the beginning of the post-incident phase. However, unfortunately, we got another page the next day for IPAM. And what we saw was that we were having an almost cyclical issue with the performance of allocating IPs. And as you can see here from this Grafana dashboard, we had a period of heightened error rates, and then we would drop down again, and then we would spike again, and then we would drop. And this cyclical behavior would repeat itself almost every day. Here's a LightStep capture that shows this. And it shows that from the beginning of the incident, which is the 28th of October, when I was paged in, and then following every day until the 8th, which was the last day of the incident, we had this cyclical behavior that occurred every day. And it was actually only fixed as a result of numerous changes we made over these many days to get our system into a better state. And so we had to go back and figure out what was going on to cause this behavior. And some new discoveries came to light. And so what we found was that there was a combination of factors at play that caused further create delays. So just to kind of give some more context on how these allocation of IPs occurs with IPAM, we have a distributed semaphore, which restricts the number of allocation requests that IPAM can take on. So IPAM usually only takes on 2 to 3 requests to allocate an IP at a time. And then once those are done, we will then take on another request. And so when we have a huge wave of requests to allocate IPs, more than we usually expect, things can start to fall apart, which is what this incident really showed. So we basically had a huge wave of creates coming in. And then we still had some overnight queries that were putting extra load on the right leader node for our database cluster. And that combined was creating this period of high error rate and high latency, and then things would kind of settle down only to spike again. So one of the things that we see at DO is that we do have some customers who will very quickly spin up a lot of droplets to complete some high computation work, and then we'll tear them down. And that was actually one of the reasons that this event occurred, is that they would create all these droplets, so sending in a huge wave of creates, and then that's coming in down to be handled by IPAM. And then on the other end, you have alpha under high load, and that is causing a negative effect on our ability to complete operations. And so you have just these two problems coming in either side of IPAM. So once again, IPAM couldn't complete operations fast enough, and IPAM actually would retry operations if they fail. So IPAM has a retry mechanism because we're the last link in the chain to finish allocating IPs and getting this droplet creation done. So if we, and then we might even retry again, which is fine. That's what we want to try and do. But when you have a bunch of requests coming in waiting for you, this can further exacerbate the whole situation. So the conclusion is that with all of this information, and so what was our solution? Well, it was actually a number of solutions that we had to deploy. And it took a long time as we tried to thoroughly test each one. So first was that we changed our retry logic to retry sooner and to also have a hard cutoff. So like I said, IPAM retries operations with the database. And before this incident, we would retry a failed operation after 100 milliseconds and then increase exponentially until reaching 10 seconds. This is exponential backoff. But that was causing issues because 20 seconds is a long time to wait. And it just was having things take too long to finish. So we changed it to retry only 3 times at discrete amounts of time. And if we fail on the third retry, we just cancel the transaction and return an error. So we basically attempted to fail faster. We also optimized our SQL queries so that there were fewer unnecessary locks when we try and read and write to the database. We also reordered the execution of some of our SQL queries. The logic to allocate an IP is pretty complex, and there, in the beginning, were 3 or 4 different queries to execute. And this is just so that we can try and amortize the cost of allocating an IP in case an IP was recently released and we can just quickly grab it. But what we found was that this ordering was not that optimal, and that it was actually causing some slow performance on our end. So we explored other options. We did some reordering. We actually removed a query or 2 that we didn't need. And then we ended up with only 1 to 2 queries being executed, and things were much, much faster. We also improved our monitoring along the way to get a much clearer picture of our system and how things looked. All told, these efforts took about 9 days to actually fully test and deploy. And the culmination of our efforts can be seen here, where we had this high latency and associated error rate. And then once we finished all these changes and made the last deployments, everything dropped and it remained consistent for hours thereafter, and it's remained consistent since then. And so here I want to touch upon the monitoring improvements that we made. So here is a screenshot of a Kibana dashboard that we put together to investigate the underlying issues during this incident and to help us with our testing and improvements. Improving our monitoring to get a better view of what was going on dramatically improved our ability to diagnose issues and to also determine which changes we made gave us the performance we needed. And so I'm going to go through each of these really quick. And the first one we have here are the errors we got by retry count. And so this really just showed us how many retries we were actually doing. And when we did this, we actually saw way more retries than we initially expected with our logic. And having this dashboard in place gave us indication that we needed to actually change our retry logic. And that's what we did to those 3 retries and then a hard cutoff. And it's been super helpful since then, just to see if any changes we make cause more issues. Then we have here a dashboard, for a graph for errors by type, and this just helps us see that when we do make a change, we can see what errors we get back, or how many errors we get back. So if we deploy something that actually degrades our performance, then we can quickly see the more errors that come back, and we can quickly roll back the change. So just having that in a visual format rather than just a series of logs really helps us quickly see what's going on. And here we have deadlocks by user. And this just really helps us see which users are causing us the most issues, and really also helps us identify any maybe bad actors that are causing certain incidents or other issues with us. And so, yeah, so I want to dig more into these monitoring changes because they've been super helpful for us during this incident and since then. Before the incident, our monitoring essentially consisted of just metrics scraped by Prometheus that was then put into Grafana dashboards. We had Kibana queries written on the fly. So one of us would go into Kibana and just write queries and see what was going on. And then we had distributed tracing with LightStep. And what we learned from this incident was that we needed to have more visibility into our database operations and error rates, which is what led to those Kibana dashboards that I just showed you. They allow us to view the status of our system at a glance and also gives us a faster feedback loop when testing performance and other changes. So actually having those there really helped us in getting a faster feedback loop on our changes and the results. And the dashboards are just more informative during incidents. They enable every team member to be more effective, regardless of how much experience they have with Kibana. And it's really helpful because in the middle of an incident, it can be hard to remember exactly which queries to write, query Kibana every single day. But with the dashboard, you can quickly see what's going on and give observations. Was a bit lacking. And we had started to make some improvements right before this incident. We had some automation to load and stress test IPAM, but we needed to actually make it a part of our process for every major change and release. And we did this after this incident just to make sure that we can prevent future incidents. And the nice thing with this kind of automation is that it couples really well with detailed monitoring and dashboards so that you can, make a change, kick off some load testing, and then look at the dashboard and see what's going on. It's very informative. So I would highly recommend teams to dig more into how they can make their monitoring pair well with their testing. But the points of testing is that you can really only tolerate the faults you anticipate and then test for. So that's why you need to do load testing and do volume testing, and then also have some tests that are specific to your system and some things you may see. So we have testing for IPAM to try and induce deadlocks with MySQL and to see if we can actually create them and what their effects are. Testing just needs to be a vital part of your system's development, and you need to invest in automation and actively explore your system's weak spots. Now I want to touch upon teamwork and the blameless culture we have at DigitalOcean, because at the end of the day, this was a very high stress situation, but there was no finger pointing. Having customers unable to create and use our flagship product is a huge problem. There's a lot of revenue at stake. But at the end of the day, it's not going to make things better to have teams pointing at each other for who's the problem and to try and fix things as quickly as possible. For this situation, we had several teams across the organization rally together, identify issues, and implement fixes. So while our service may have been at fault, quote unquote, we had teams working on fixing their queries to run on the read node instead of the write node. We had other teams that were showing us how to improve our monitoring. Everyone just came together to help us out. At DO, we have an internal PIR or post-incident review process in which we document every incident and then post that publicly in the organization so that we can all learn from the incident and look at our own systems more critically to see if that incident would occur elsewhere. At the end of the day, what I learned from this is that software is hard at times, and no one can predict every incident that could occur. If an incident does occur, it should be regarded as a process issue, meaning that there is likely some improvement in code review or engineering practices that needs to be made. Reliability work needs to be more prioritized. And also documentation should likely be improved upon. Documentation is here because this whole change in the isolation level of our database transactions was something that actually had occurred previously. If you remember in the beginning of my talk, I had said that IPAM came about as a split off from another service that used to handle IP address management. And that service had a similar incident occur way back in the past, and they made that same isolation level change and it fixed things. But that change wasn't documented in the IP address management to a different service. They didn't know that they should have had the isolation level at recommitted. So it's important to document all major technical decisions, just in case of future transitions of services and logic. And so we're going to end with the takeaways from this talk. Good monitoring makes distributed systems easier to build and maintain and debug. Always test your patch even when under pressure. And if you feel like you can't do that right now, then really try and advocate for that as a process change. Document every major technical and design decision for future transitions. When working on big systems, ensure that you're setting time aside for reliability, maintainability, and monitoring work, and don't have everything just focused on feature work. Because if you don't put in the time regularly for these kind of things, then you're going to be scrambling when an incident occurs, and you might even hold off on feature work for quite a while as you put into place reliability, maintainability, and monitoring. Advocate for a blameless culture and always learn from incidents and take them with you. You'll never avoid every bad scenario or late night page, but good engineering practices and improvements can decrease their likelihood. And as always, have your metrics, SLOs, and SLAs drive your reliability efforts. Because if you don't know where you should be devoting your time, you might just be spinning your wheels. And that comes with having really good monitoring in place so that you can know the numbers to improve. And finally, my personal learnings from this incident: observability is super important, and you should prioritize it as part of working on a service. Learn your system's hotspots and how you can improve upon them, and also learn about the failure modes of your system. If you don't know your failure modes, then you won't know how to prevent them. Always work on your documentation just to help any engineers who are hopping onto your team or trying to help you out. And invest in test automation so that you can effectively explore your system's hotspots and failure modes and just have an understanding of how well your system is operating. And always try and improve the quality of your engineering, both as an organization and with the services under your responsibility. And one last takeaway that I want to add here is that if you're going to give a conference talk, then make sure that you are either off call the night before or that you have a teammate cover for you, because you don't want to be paged at 4 a.m. the morning of. Thank you. And that is my talk. I would love to take any questions now.